Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And we're in a little mini series that I'm calling Split Plot Design, and we're in part 7 of 10. And here we're going to look at the expected sum of squares. So for model split plot RCB, so randomized complete block design. And I would encourage you to watch part 1 and part 2 for more detail of why I call it that. Now the model is this: mu plus y ijk is equal to mu plus alpha I plus beta j plus the error term, whole plot error term, gamma k, the interaction term, the split plot error term. Both are normally distributed, mean 0, and their respective variances. The expected value of y, now remember this is a vector, is x beta star, and the variance of y is this. And in part 1 and 2 we drive this a little in more detail. Sigma squared is the combination or the addition of the two error terms. Rho is the correlation between the error terms. And this is the interaction, or not the interaction, it's the perpendicular projection matrix onto the interaction space of alpha and beta. Sometimes people will just call this a W, so it's onto the whole plot part, of the design matrix. So the expected value of the sum of squares alpha. Now the sum of squares alpha is defined like this. It's y transpose m alpha minus j y. Well, this is the perpendicular projection matrix onto the column space associated with alpha, and this is the perpendicular projection matrix on the column space of 1s. Now I have a video out called Expected Value of Quadratic Forms, and there we derive the formula that we're going to use, which is this. It's the trace of this matrix times its variance. But since that's a constant, it can come out of the trace. Then it's the expected value of y times this matrix times the expected value of y. Don't forget the transpose. Now we start simplifying this expression here. So here we take that times I and we just get it back, and then this times this matrix we get it back because it's actually part of the alpha column space. So then we write factor out of m alpha minus j, and then the constants out front, and it's the trace of this. And the trace is t minus 1, so that's where we get this t minus 1. Oh, my cat's going to come up, I can already tell. So then here, since this is a perpendicular projection matrix, it's idempotent, so we can, and it's symmetric, so we can take it times itself, take one of them into this one, and that's what we get here, and then this comes down. Now on this next step I just keep this the same because I'm running out of paper going horizontally here. Now this is m alpha minus j, and the x I expand into their respective column spaces. The beta star comes down. Now, and this is it. So this is the answer. But we're going to try to simplify this into a scalar format. And so this expression, let's call star. Now, what I'm going to show you here, on this side, also applies to this side. So this matrix times 1 is 0. This times alpha, it's whatever it is. And this is orthogonal to x beta, so we get 0. It's orthogonal to, this is orthogonal to x gamma. And then this is, whatever it is. And the same thing applies to over here. So that's why we get this expression. But this is vector product. So these zeros can, that times this plus this times this plus this times this, the zeros don't contribute, so you just remove them and then bring down what's left here. And now this beta, notice that when it gets multiplied times this expression, only the relevant piece is retained. And so that's why we have this. Now, from part 4, we expand what this is in scalar form and this too. And it ends up being this sum. It's r times m, the sum from 1 to t of this expression here. Now, if you were to look at, so Montgomery's book, they have just this expression, alpha I squared. They don't have these terms. And the reason is, in their book, they use what are called side conditions. And they assume that this is 0, and this is 0, and this is 0. So the only thing left is alpha I squared. So if you don't use the side conditions, this is what's left over. So the expected value is this piece plus this piece. And I'm not going to rewrite it because I didn't want to waste paper. But now if we look at the expected value of the mean squared error, or mean square for alpha, it's expected value of the sum of squares divided by t minus 1. So the t minus 1 can come out front, and then the expected value is this piece plus this. So the t minus 1's cancel. We're left with just this. And then you divide this by t minus 1. Right? And now this is going to play a very important role in hypothesis testing. Now, in Montgomery's book, he assumes that these are all 0. But when you don't have the side conditions, you have to assume that all of this combined is 0. And we'll get more into that in a later video. Now, the expected value of the sum of squares for beta, now it's this by definition, and we derived the partitioning of the sum of squares in the previous video. Then the formula for the expected value of a quadratic form is the trace of this matrix times the variance of y. That's what this is. Of course, the sigma squared, it comes with it. The mean of y transpose times this matrix, mean of y. Now, when you multiply this in, then you can write factor out of m beta minus j, and then that constant comes out front. I'm skipping some steps, but trying to give you the gist of it. Now this matrix times each component of x. So what we have to do here is when we expand x like this, and then take m beta minus j times each of these, which is what that x is, they all drop out except for the x beta portion of that design matrix. And then when this is multiplied times all those zeros, we only get the beta left. So we're left with the product of these. And this product can be shown to be this sum right here. So this is for the block effect. Now, when we find the expected value of the mean squared for beta, then we divide by r minus 1. And this cancel, we're going to have an r minus 1 here. That's what we do on the next page. So the mean squared for beta is this piece, and then it's, of course, r minus 1 divided by what we derived previously. And these expected values, look at this this piece here. You know, it has both of the components, the split plot error and the whole plot error. And that's going to be an important aspect when we look at f-test. Now, the expected value of the sum of squares for whole plot is this. We derived that in a previous video. So it's the trace of this matrix times the variance, the mean of y times this matrix, the mean of y. Don't forget the transpose. Then this matrix times each component of x drops out. It's orthogonal to each component. And we looked at some of that in part 3. So what's left over here is it's the trace of, ends up being this matrix, and then the constant come out front. And the trace of this matrix is t times r minus t minus r plus 1. So then the expected mean squared error for whole plot is the expected value of that sum of squares divided by this here, which ends up being the degrees of freedom. So this cancels with this, and we're only left with this piece here. Now the expected value of the sum of squares for gamma is this, so y transpose m gamma minus j y. And again, we break it into our formula here. That matrix, variance, mean, that matrix, mean, and then this times each of the components. The parts that don't drop out are the x gamma and the alpha gamma components. Otherwise it's 0. So then we just get this matrix. And when we multiply it together, and this over here ends up it ends up being sigma s squared m minus 1. So then this piece is this sum, or this sum here. So this comes down, and it's t times r times this expression. And again, if you were to look at Montgomery's book, these pieces with it using his side conditions are 0. So you just get gamma squared, gamma k squared. But if you don't use side conditions, it's this. Now the mean squared for gamma is you divide the sum of squares by n minus 1. And so, you know, that cancels the divisor, and we're just left with this. And then this piece is divided by n minus 1. And this is exactly what Montgomery has, but these are 0 with his side conditions. Now the sum of squares for the interaction term is this. And again, using the formula, this matrix times the variance times the mean of y transpose, this matrix, this times this. Then here, when you multiply it in, you end up with this expression here. And I'm skipping some steps to keep the video at a right length, but trying to give you enough that where you could do it on your own. Then this matrix times each of these column space is 0, except for that last one, the interaction space, right? And then it has the right parameters of this vector. When you multiplied it down, you just get this. So then this vector product ends up being this double sum. Well, it's whatever it is, but then I skip here and I just go straight to the mean squared error, which is the sum of squares divided by this piece. So then you're left with this, and then of course you divide this piece by t minus 1, m minus 1, and you get this. So that's the interaction between alpha and gamma. The expected value of the sum of squares for split plot is this. And then again, you use the formula, and then this times each part of the subspace is actually, they're all orthogonal, so it all drops out. And when we do the R software illustration, all these matrices times each component, we're going to illustrate and show that they are indeed 0. It's kind of neat how it all works out. So this is the expected value of the sum of squares error for split plot, and then the mean squared error is for split plot is it's the sum of squares error divided by this right here. So this, and then you're just left with the sigma s squared. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.